And we have Christopher coming up from hunting. And then we'll have a 10-15-minute coffee break after that. So you're okay with the point? Yeah, I think so. Yeah. Well, thanks very much. Okay, over to you.
Right, good afternoon. Thank you for having me. So a little bit of a change of pace. So we're talking about some an enhanced oil recovery technology that isn't necessarily new, but over the last couple of years, we've seen some excellent results that I'll be sharing with you today. So, as an operator, what do you want, right? What are you looking for? We want to lower water cut, right? Improve economic return and ultimate recovery. Reduce H2S. Obviously, that's a big problem in places like Norway, the UK, CS, West Africa, Southeast Asia. And ideally improve your economic return with existing assets, right? And what I'm explaining today is a technology that does all of that, requires zero capex, and it's very, very simple application, whether it be offshore, onshore, and FPSO, subsea, and we've done it all. So also proven globally, right? We have well over 600 applications now, closing in on 200 reservoirs around the world. And extensively proven both onshore and offshore on every oil-bearing continent. So, how does it work? So, the main aspect here is that we're using only resident microbiology, right? So, we take a sample first to understand what's there. We can differentiate between what was sedimented when the reservoir was formed initially. So, microbes, both bacteria and archaea, that have been there for millions of years, and also through contamination, through the drilling process, water injection. All these things change the way your reservoir looks from an ecology perspective. Now, importantly, if you don't have the microbes that we need in the reservoir, there's nothing we can do. We don't inject anything. We don't inject any microbes. We only inject a nutrient to feed the microbes that already exist there. Through doing this, through applied microbiology, we can change the ecology over time to narrow. So, for example, I'll show a couple of examples, but you'll start off with 50, 70 unique species, say, in your reservoir. And after a year and a half, we'll narrow that down to 9 as throughout competition, right? So we encourage the microbes that we're looking for to grow, and they naturally outcompete the rest, as in any biological system on Earth, right? So by reducing the water cut, we obviously decrease lifting costs, significantly increase recoverable reserves, averaging between 5 and 8%. Has been better in the past, but usually about 5 to 8%. And also can reduce the chemical spend on H2S. And importantly, the recovery that we're looking at is completely, well, is truly enhanced. It's not accelerated like your traditional chemical EOR types technologies. Right, so the main difference between other types of EOR that you'll be looking to implement and us, I suppose the main one is CapEx, right? We don't require any storage facilities, any pumping, any permanent pumping or separation facilities. It's a light touch. We do 4 batch treatments at a maximum in a water injector per year. And that's all that we look to do. The nutrient we use is extremely environmentally friendly. We have all of our gold standard certifications around the world in all geographies. And we've been successful now recently. Actually, we've got an application happening next month on an oil field that has an original bottom hole of 157 degrees Celsius. So again, that's only possible if it's been under water flood in an area like the North Sea with cold water for a long period of time, where you have a large amount of water temperature gradients between the injectors and producers. But again, really our unique selling point and where we have a competitive advantage as a technology is the fact that we can implement this in any offshore field with your existing assets and no changes to any topsides or any facilities. Right, so quickly I'll go over this. The sweet spot is quite wide, right? So we've on those 200 plus reservoirs we looked at, we've been successful down to 12 API. That's in the Middle East and Canada, and as high as 48. Essentially looking for black oil. Relatively neutral pH, although that's not necessarily defining. reservoir temperatures of less than 121 and salinities of less than 240,000 ppm. Now, those two are the main characteristics, right? As you go up in temperature and as you go up in salinity, the natural diversity of your microbiology ecology diminishes, right? So microbes that live above, say, 140,000 ppm are called strict halophiles, right? They want to be in high salinity environments, and above 95 degrees Celsius are hyperthermophiles. Now, the amount of species out there that are both hyperthermophiles and halophiles is very, very small. So really, it's like a triangle. The further you go up in salinity and temperature, the less diverse, the less we can do. And then ideally looking for oil fields under active water flood, right, and a permeability of greater than 1 millidarcy. The data that we need is essentially as much as possible, right? As with anything, the more data you get, the better you can design treatments, and certainly base the frequencies of our injections on hopefully very good data that we get from the customer. Right, so going over the mechanism. So this process that you see here, where you get larger droplets being formed into smaller micro droplets, there's no chemistry at play here, right? This is a purely physics problem, right? So 99.999%, virtually 100% of the microbes in an oil reservoir are hydrophilic by nature, right? They want to be in the water phase. Now, certain species that share a very specific gene in their DNA and sometimes in RNA actually allow for them to change morphology. So they polarize their cell walls, they become hydrophobic instead of hydrophilic, right? Now, they do this because they're cockeye or rods. They don't have any phalanges in the tail, they can't swim. So after 10,000 years, 100,000 years, they need to move into areas that are more nutrient dense, right? This process happens slowly though, over thousands of years rather than days. What we've been able to do is identify a specific set of nutrients that can limit them faster. So that change in morphology is happening due to a phenomenon called specific nutrient limitation. What we can do is essentially give them 10,000 years worth of food in one day and speed up that process of changing morphology from 10,000 years to 7 days, okay? And so doing, we increase the number of microbes in the water phase locally, first of all, on a producer well by, a factor of 10 to the 3, 10 to the 4, sometimes more. But then we only put a small amount of nutrient in because we need them to starve, right? They need to go into that nutrient limitation phase. So when they do that, they change morphology, they move out of the water phase into anything that isn't water, right? It's not like they're attracted to the oil specifically, they're moving out of the water into anything that isn't water. And so doing, they form around the oil droplets, basically physically reducing the IFT from in the water droplet section here to reduce the oil droplet size, improve the mobility, improve the relative permeability of the reservoir, and also getting in between the oil and rock, right? And the microbes we use as well do not form biofilms. For lack of a better word, they're not sticky like the biofilms you see on your casing or umbilicals or near wellbore. It's a single thin layer of microbes that get between the oil and rock, and then in so doing artificially or physically making a barrier to improve the wettability of the reservoir too, which is why we've had very good success on both sandstone, carbonates, very heavily oil wet fields as well as very water wet. So counterintuitively, the rock and the reservoir plays very little. It's actually of no consequence really into how well the technology works. It's more about the strength of the ecology at the start. If a large proportion of the microbes in your reservoir exist already that we can use, then this process works better, essentially, right? Because we're getting a head start on changing the reservoir's ecology. Right, so one other aspect that I talked about was our competition. So if your reservoir, if of all the reservoirs we've treated, if it has H2S because of bacterial-induced H2S, right? That's sulfitogens, sulfur-reducing, thiosulfate, sulfate-reducing bacteria. We have a 100% track record of reducing H2S. It has to. If we're increasing one specific species of microbes, they have to outcompete the others. There's no any biological system on Earth that's counter to that, right? So what happens is, it's rather complicated on the microbiology side, but essentially, SRBs, or reducing bacteria, have a different food source to the microbes we're interested in, but they share life forces, right? Similar to humans and trees. We eat very different things. We would die if we eat fertilizer, to any sort of level, but we both need sunshine or sunlight, right? To get vitamin D and for chlorophyll. So what we're doing is we're feeding this one of them to grow substantially as a proportion of the other and outcompete the other for the life forces. And eventually we reduce their metabolism slowly and eventually kill them off over time. So in this case, this is a published paper, so I can say this is CNOC in the North Sea, very characteristic of increasing H2S through the injection of seawater. From a single injection, though, we've reduced H2S by more than 50% for over 4 years. We've moved to a different part of the reservoir for a full field application now, but that was a very good example. And again, repeated for another major in the North Sea. I don't know if you could see that very well, but prior to the treatment, almost 70% of the population was sulfitogens, right? Once we did the injection, we did the shut-in, flow back, it went down to 0.6 and then eventually to 0.12% of the population. So this is one of our better results ever. We've basically proven that we've completely obliterated the population of sulfitogens in the reservoir. And that's localized in this case to the near wellbore, but obviously it expands and it gets bigger as we go through the larger volume treatments between injectors and producers. Again, another operator in the North Sea saw a reduction of 83% within the first 5 months after treatment. So this is something that happens every time. It's not something that we sell as the main driver. Usually it's improving oil recovery with a byproduct of reducing H2S, right? Although not always, some customers look to do H2S treatments specifically. Right, so I'll give you one example. I mean, if, of course, you are interested to hear more, we have, as I said, hundreds of analogs we can share with you. So we try to history match not only the ecology, but the reservoir too. In this case, this is a field in the South Oman. It is around about 20 API. It varied from 17 to 21 across the field. And 55 to 60 degrees Celsius, which is a very good range for our technology, and pretty fresh water, almost to 13,000 ppm. So these are the samples we take, basically. So just as an example, this is all that we need from a reservoir to tell you if it's going to work or not, basically. Right? Because we do the lab work in the lab at reservoir conditions, right? And the key fact here is that these microbes don't want to be in a lab, right? They've been in the oil field for a very long time. That's where they want to be. So if we can get this process to work with sampled water in the laboratory, we're very, very confident that in the field it will work better. And that's what we see the vast majority of the time. And the nutrients come in IBCs for small wells. This is an onshore well. But they come in IBCs or large ISO tanks, depending, but the volumes are very small. In this case, the injections in the injectors, number 26 and 11, were only a few thousand liters each for each batch, right? Small field. I'll get to the production soon. But that's what we're looking at, right? So the operation could vary on an offshore field. It's usually just a pumping spread and a few IBCs, and you hardline the water injection to the producer, or if we're doing an injector, we just spike that across. Onshore, it's just a pump truck and a tank, right? So what happens is we will deliver the nutrients to the field, regardless if it's offshore or onshore, in partially filled tanks. We mix that up with a little bit of deionized water and either spike that into the injector well or mix that again with produced water and inject into a producer. It's very simple. There's no special mixing required. The nutrient is water soluble and comes at the same specific gravity as water and acts as water. So, and everything is done, as I say, in batch treatments. The injection is usually done quite slowly as well, about 1 to 4 barrels per minute. Can be increased on larger wells. For example, the North Sea, we're doing a few wells that are like about 50,000 barrels of water injection a day. And therefore, we have to do it a bit quicker because we'll be there all month, basically injecting if we don't. So over the first year, so we'll start off on the left-hand side. This is what the oil field sample looked like beforehand, right? So we're staining for these specific species that we're interested in through the analysis in the lab. So before and after, pretty clear something's happened. What happened was we got a 4 to 5-fold increase in overall microbes numbers of the ones that we're interested in. There were 2 injectors, six producers. The injector line is fed from a tank, so the same amount of water injection every single day on both injectors. And at the producers, we saw a 40 to 150% increase across those 6, depending on the well. On the line here, you can see that first line, we did 2 pilot tests on 2 producers. So I won't go into how it's actually much time, but essentially you sample, you do a producer pilot, very small volume just to prove it, then you move on to the water injector, right? And in this case, we did 2 wells, we got a little bit of bump from those 2 wells, and then started doing the batch treatments on the injection. What that meant as a field, we increased production across the entire pattern, so 2 wells, 6 producers, by almost 70% as a baseline. So at this point here, we're 70% above baseline, which economically meant that for a field that was producing on a baseline of 800 barrels a day, we produced incremental oil of almost 120,000 barrels. So that's on a field that's against 800 barrels of injection. It was very, very good results, of course. We've expanded to all of their fields now, which is good, but essentially this is all that it takes, right? So as an operational perspective, each one of these injections lasted like 8 hours. So you're looking at, in the first year, we were on the oil field for 24 hours out of 365 days, and improved production by 70%. And that again is because we're only using a small amount of nutrient to try and tweak things. We're not trying to change the overall ecology. We're only trying to give a small competitive edge to the certain species so they can proliferate overall. And eventually, over time, the ecology will become so strong in favor of what we're looking for that these numbers of injections actually decrease. So year 2, we're actually only going to be doing 2 or 3 injections, not 4. That's just to keep it topped up. On an individual level, so these are the wells that make up that whole overall graph. You can see very clear cause and effect. The wells are pretty tightly spaced, so we saw as quick as 3 weeks travel time in the nearest producer. So luckily we got some very good, very instantaneous almost results from these applications. And again, the same thing here. This is where this was one of the pilot wells, did the pilot well, and then carried on and sustained improved production. The one interesting part of this application was the fact that one well that was shut in for a couple of years, due to the fact that it had 100% water cut for almost 3 years whenever they did a well test on it, pretty much, and a 99% water cut. So they shut in due to not being able to economically produce. We got that water cut down from 99 to just under 80, about 77%. The water cut is now as I speak, and that's something we've replicated a lot of times all over the world. So it's another unique aspect of the technology. It can be economical to even just use on completely watered out patterns or wells. And that's everything. I didn't actually include a thank you slide, so I'll just say thank you very much. So that's everything I've got to say. I mean, there's a lot more to go through. I did try and speed up for time's sake. So if there's any questions, please feel free to ask.
Sorry, I don't mean to keep hogging the microphone. Thanks a lot. Very interesting presentation. Again, another question from a position of ignorance.
Yeah.
Just visualizing it and not thinking about it too deeply. When you're munching up these the oil to smaller droplets, I'm aware that emulsions and things like that more of a problem. I mean, I maybe it's a completely different scale problem, but I know I hear people moaning on about we have an emulsion problem and tripping things on the process plant and all that sort of stuff that I don't really understand. But this kind of stuff, does it give you more emulsion problems, or you're not doing it at that sort of scale that would give you problems?
Yeah, good question. I think you put your chemist hat on. That's the question I get every single time I meet someone. The answer is no, right? So these microbes, we've never, in those applications we've done, we've never seen an emulsion on the surface. And that's because it's not possible biologically, again, thankfully. These microbes that work, they're only in the reservoir. First of all, they can only work at that temperature because microbes, like all animals or mammals, well, all actual living life, can live in a very small band. But there's species and there's strains that can push the envelope, but most microbes can only live in like 5, 10, 15 degrees maximum. So first of all, from a temperature perspective, when they get to the near wellbore, and certainly when they get on the way to the surface, they can't perform this function anymore. And the other thing that adds to that is they're all strict anaerobes. So when you get to the surface again and you start introducing oxygen, introducing some, you know, the mixing and the separation, they cannot perform their function. So this is strictly temporary. It's never something we've ever seen on the surface. It's really more of a reservoir level. By the time it gets to the near wellbore, this oil really has been released, and some of it will coalesce back together. But certainly, by the time they get to the near wellbore and up the bore, they cease to perform this function. So it's not something we've ever seen.
Thank you.
Yeah, there's one from online now. Yeah.
Yeah.
Thanks. Question from Amy. Does the chemical work in low pressures and depleted reservoirs, for instance, less than 800 psi?
Yes, it has, but there has to be displacement, right? So we've seen some really good results from a microbiology perspective in some reservoirs without water injection. And then the only thing that we can submit is that we know that the process has taken place because we take samples after we do the injection, right? So we see that the microbes have changed their morphology. And they may have released oil, but if there's nothing pushing that released oil close to the wellbore, then there's nothing, I mean, you're never going to produce. It'll look like that. It'll just stay like that forever, right? So that's why we really prefer the water injector pattern. So at least, even if it's low pressure, at least you get something moving from A to B, right? And yeah, we have had some success in really low pressure reservoirs, but again, I think that has to have some sort of water flood.
Great. Go ahead. Another one from the room. Yeah.
Yeah, hi, Adrian Geyer. Perhaps a silly question,
Yeah.
but from what I understand, you're saying that the microbes can't live beyond the reservoir, but when you flow the well, you're going to have a load of dead microbes in your oil. Is that being silly? Or if you do have a load of dead microbes in your oil, how do you get rid of them?
You've got that already, right? So remember, we're not changing anything. The total microbial load of your reservoir stays the same. We're not putting enough nutrient in to make your entire reservoir to have 10 times more microbes. All we're doing is putting enough in to change the proportion of the ones we're looking at. And so this is the beauty, I suppose, as well, of using resident microbiology. There's zero compatibility issues, because they'll ask me, some customers ask me, is there any compatibility issues? So do you have any issues now? Because you're producing every single one of those microbes that we're gonna be using. So really there's no change in total microbial load, just the proportion. And it won't be in the oil phase anyway, it'll be the water. So that sort of gets separated out. You know, but you did bring a good point up about them dying. They don't necessarily die, right? So what I said is that they stop performing their function. So most of them will spore, right? So they go into like a hibernation state. And it's really interesting. I mean, every single reservoir we sample in the North Sea have got some really unique bacteria and archaea. One specific one in Norway, was one that we found that is the microbe has only been found at the bottom of the ocean in thermal vents in the Caribbean. It's the only place in the world that's ever been seen. So what's happened is those microbes have come to the surface, spored off, been carried by the Gulf Stream and through to the North Sea, picked up by the injector, injected into the reservoir and gone, right, this is brilliant. Anaerobic conditions, hot, and I'm back. And so that was like 25% of the ecology. So microbes can do that, right? And there's very, very large proportion of reservoirs in the North Sea that are below 70 degrees Celsius. They've got a very high proportion of Marinobacter, right? Which is microbes that live slightly below the level of the ocean. And those are microbes that are facultative anaerobes, which can, again, once they're in the reservoir, sort of come back to life. And we see a lot of that too, specifically in reservoirs that are between 40 and 60 degrees Celsius. So, yeah, look, you know, this is the first 4 years of this was trying to get to win over chemists, because we talked to them about bugs. You know, that's their backs go up and they think I'm gonna have to spend millions on chemicals to kill everything. But luckily, anything you do with the reservoir, certainly with biocide, only acts on the wellbore, really, right? You couldn't pump enough biocide to kill the amount of bacteria that you have in your reservoir. I mean, the average number in the North Sea so far, I think, is about 3.5 million microbes per milliliter. So in the reservoirs in the North Sea, 3.5 million microbes per milliliter. And the thing is, no one's sort of paying any attention to that. So